Hello, everyone. Thank you for joining this session. I am Ryuichi Yamamoto from LINE, and this is the title of my speech. Let me first introduce myself. I joined as a speech processing engineer right when LINE opened its Kyoto office in 2018. After working at the Kyoto office for a while, I went to Korea to collaborate with the NAVER team. And I returned to Kyoto, and that's where I work now. Although I've worked in different places, I have always been working on speech synthesis. I do open source development as a hobby, and since before joining LINE, I've published and maintained speech tools such as speech synthesis and voice conversion tools. I love speech, and that's what I do both in my work and my private life. Today, among the researches of speech synthesis at LINE, I will talk about the method called parallel WaveGAN, which was adopted at ICASSP. However, unlike the presentation at ICASSP, I would like to explain about the background in detail so that a wider audience, including non-experts, can understand what speech synthesis is and its challenges before I explain about parallel WaveGAN. First is text-to-speech, TTS. Simply put, it's a technology that allows a computer to speak naturally like a human. As shown in this figure, when text information is input to a computer, the corresponding speech waveform is output. It is often simply called TTS, short for text-to-speech. This technology called TTS has been used in many applications, including smart speakers in recent years. For example, at LINE is CLOVA, a virtual assistant jointly developed by NAVER and LINE, which uses TTS to interact with users and read news aloud via CLOVA. Another example is a device from Gatebox with three-dimensional characters that you can talk with. Our technology is used in synthesizing the inflectional and lovely speech of this female character. Please watch this demo of a user asking for weather information. How was that? I hope you saw that our technology can synthesize very cute and natural speech. A more recent example is LINE AI Call, an automatic telephone answering service. It is a service created with the idea of automating the call center work. The mechanism consists of a complex set of technologies, including automatic speech recognition of users' responses, text analysis, and speech synthesis to give responses. There's a demo of AI staff taking a reservation from a customer. So this is the telephone answering service that was realized jointly with Ebisol. It showed our TTS technology being used in a service. Moving on to the technical topic, let me explain the technology behind TTS, text-to-speech. There are various types of TTS mechanisms, but this figure shows a relatively simple system that has become mainstream recent years. There are mainly three components. From the left, text processing, acoustic model, and vocoder. I will explain each in order. First is text processing. The purpose of this module is to convert the input text into a format that the synthesis engine can read. Processing such as text normalization, grapheme to phoneme, and accent estimation in Japanese is performed. The text is converted into phoneme sequence or linguistic features. Next is the acoustic model, which converts the linguistic features into acoustic features. Acoustic features include pitch, voice quality, and length. The method used recently is called Mel spectrogram, which converts the sound spectrum into a scale suitable for human hearing called Mel scale. Last is the vocoder. In recent methods using neural network, it is also called neural vocoder. This module takes the acoustic features as input and outputs speech waveforms. Today's talk will focus on this neural vocoder. When creating service using speech synthesis framework, the neural vocoder tends to become a bottleneck in both quality and speed. We thought it was important to improve this module and developed the new method called parallel WaveGAN. Before talking about parallel WaveGAN, there is an essential method in neural vocoder. That is WaveNet, which was proposed by Google in 2016. WaveNet, as the name implies, is a neural network that generates speech waveforms. It is an autoregressive speech generative model in which a speech sample at time t depends on all speech samples up to time t-1. Based on this model, WaveNet generates speech samples in sequence from the beginning. For a second of speech, it generates 16,000 samples of speech waveforms per second. For a higher quality speech, it generates 24,000 or 48,000 speech waveforms per second. It may seem like a naive and inefficient approach, but it has attracted a lot of attention because of its overwhelming quality. This shows the result of subjective evaluation. The higher the value, the more natural the speech is. The two on the left are the conventional methods, followed by WaveNet, and on the right is the natural speech. As you can see, WaveNet is much higher than the conventional methods, although not as high as natural speech. We have shown that WaveNet can generate high-quality speech. However, as I will explain, there are pros and cons to everything. Speech waveform generation methods can broadly be classified into two types. One is autoregressive generation methods, such as WaveNet, and the other is non-autoregressive generation method. The autoregressive method is an approach in which speech samples are generated one by one in sequence, as explained earlier. On the other hand, the non-autoregressive method generates speech samples of all times in parallel. As a leading method, there is parallel WaveNet and its variant, Clarinet. I would like to compare these methods. Please look at these numbers. These show how many seconds it takes to generate a second of speech. With an autoregressive model like WaveNet, it takes 180 seconds or 3 minutes to generate 1 second of speech. No matter how good the quality is, this cannot be applied to services. On the other hand, with the non-autoregressive method, by using hardware for parallel computing such as GPU, you can generate 1 second of speech in about 30 milliseconds. This is fast enough to be applied to services. As I just explained, the non-autoregressive method can achieve high-speed speech synthesis using GPU. However, it is generally said that it is lower in quality compared to autoregressive method. In addition, the leading non-autoregressive method called parallel WaveNet requires training of two neural networks called teacher and student, and the training is difficult. Therefore, we have been doing research to solve this issue and to establish a method that is high speed, high quality, and relatively easy to train. The introduction became a bit long, but The research result is parallel WaveGAN. The name depicts how we solved the issues. First is parallel, a non-autoregressive model that enables fast speech synthesis. The second is WaveNet. We apply WaveNet, originally proposed as an autoregressive model, to a non-autoregressive model with a little modification. As a result, the goodness of WaveNet's model is inherited. The third is GAN. By adopting a method called GAN, high-quality speech synthesis is achieved without the teacher-student two-step training of the conventional method. Training GAN is known to be difficult, but an auxiliary loss function called multi-resolution STFT loss plays an important role in stabilizing training. Now, let me explain the technical details. First, I will explain the model structure of parallel WaveGAN. Here, the upper half shows the conventional WaveNet. The lower half shows the parallel WaveGAN. WaveNet's model consists of a deep convolutional neural network with 30 layers. By combining a deep neural network and a technique called dilated convolution, it is possible to capture long-term dependence in the time direction of speech waveforms. To explain the specific behavior of the model, WaveNet receives input of speech up to time t-1 and generates a speech sample at the time t by the convolutional neural network. The generated speech sample is then fed back to the input, and the neural network generates a speech sample at time t+1. WaveNet generates speech by repeating this process over and over again for the length of speech. Next is parallel WaveGAN, which has almost the same model structure as WaveNet and is composed of 30 layers of deep convolutional neural network. The big difference is the input and output. The input uses a noise vector of the same length as the speech. The noise vector is processed in parallel by the neural network to generate the entire speech waveform at once. It's very simple. You may wonder, will this simple method work? The key is the technology called GAN. You may have heard of GAN for its ability to generate high-quality images. GAN is a framework for acquiring a generative model by making two neural networks, a generator and a discriminator, compete each other. The generator takes noise as input and generates a fake object. The discriminator takes real and fake objects as input and learns to correctly classify which is fake and which is real. The generator is trained to generate a more realistic object so that it can deceive the discriminator. By repeating this process, the generator will be able to generate natural objects that is indistinguishable from the real objects. So that's the mechanism of GAN. GAN is known for producing images that look real, but in some cases, you may not get the result you want. This is an example showing the result of solving the task of converting a human-drawn picture into a realistic photo using cycle GAN, a model for image domain conversion. First, please look at this pair. When you train using the pure GAN framework, the result is that it is converted like a photo, but the color is not preserved. This can happen because the GAN training criteria have no constraints related to color preservation. One solution to this problem is to design auxiliary loss function and optimize the loss function at the same time. In cycle GAN, auxiliary functions such as identity mapping loss is used. As you can see from this pair, by using auxiliary loss, the style is converted and the color is preserved. How can we apply GAN to speech? Our preliminary experiments showed that high-quality speech synthesis is difficult without auxiliary loss functions, so we designed auxiliary loss functions specially for speech. This is where the idea of short-time frontier transformation (STFT) comes into play. I will not talk about the calculation method of STFT, but for one-dimensional speech signal as shown at the top, this method gives a two-dimensional representation of time and frequency to show how the frequency component changes over time as shown at the bottom. For clarity, the log is taken to be shown in decibels. Speech features vary depending on individuality as well as the type of phoneme generated, but can be well represented in time frequency, such as STFT. Using this STFT, we designed two types of auxiliary loss functions. The first loss function is called spectral convergence. From the left, the STFT of natural speech, the STFT of speech generated by the generator, and their difference are shown. The graph on the right shows that the low frequency and mid frequency components with high power are emphasized. By using this spectral convergence loss as an auxiliary loss, the generator is trained to reproduce high-powered components centered on the low frequencies of the speech. The second loss function is called log scale STFT magnitude loss. The difference from the first loss is that it takes the log of STFT. From the left, the log STFT of natural speech, the log STFT of speech generated by the generator, and their difference are shown. If you look at the graph on the right, you can see that the high-power components are distributed throughout the mid-wide band of speech. By taking the log, the difference is emphasized even in the frequency band with small amplitude. By using this log STFT loss, the generator is trained to reproduce the detailed structure of speech. In other words, the STFT loss explained earlier and the log scale STFT loss are in complementary relationship. There is another tweak when designing the final auxiliary loss. Specifically, the two loss functions explained earlier are combined as multi-resolution. In fact, there is a trade-off between time resolution and frequency resolution in the time-frequency representation based on STFT. For example, if you try to increase time resolution, as shown on the left, the frequency resolution will become rough. If you try to increase the frequency resolution, as shown on the right, the time resolution will become rough. To solve this issue, the simple solution is to combine different time-frequency representations. In the case of parallel WaveGAN, three types of STFT loss are combined as shown here in order to prevent the generator from overfitting into one time-frequency representation. The final auxiliary loss function can be expressed by the sum of spectral convergence loss and log STFT loss with three resolutions. Now, let's take a look at the process of training parallel WaveGAN. As explained earlier, GAN has two models, generator and discriminator. First, the generator takes random noise and acoustic features as inputs to generate speech waveform. Then the discriminator is trained to take the generated speech and natural speech as input and correctly identify whether it is real or not. Next, the generator is trained to minimize the sum of the STFT loss with multiple resolutions and the adversarial loss caused by the action of trying to deceive the discriminator. By repeatedly training the discriminator and the generator until there is a convergence, the generator will be able to generate speech waveforms that are indistinguishable between real and fake. That is the training process. Next, this is the experiment. In the evaluation, the first focus is the neural vocoder in the latter stage of the overall framework of TTS. Again, a neural vocoder is a module that takes acoustic features as input and outputs speech waveforms. As the baseline for comparison, WaveNet was used as the autoregressive type, and Clarinet was used as the non-autoregressive type. Next is about database used for this evaluation. We used recorded speech data of Japanese female speaker. Here is the sample of the speech. The training database contains about 11,500 sentences, which is about 23 hours in time. This is the result of the experiment. We studied the effectiveness of the auxiliary loss function we designed. This shows subjective evaluation. From the left, a method using a single STFT loss, a method using multi-resolution STFT loss, the natural speech. As you can see, when the auxiliary loss is not enough, the score is very low. But by using the multi-resolution STFT loss, it is significantly higher in naturalness. From this result, we were able to confirm the effectiveness of the auxiliary loss function in speech generation using GAN. Now I will play the speech samples in the order of natural voice, natural speech, single STFT loss, and the multi-resolution STFT loss. How was that? By using the multi-resolution STFT loss, the subjective quality is greatly improved. Next is the evaluation result of inference speed. This shows the result measured on the server using NVIDIA V100 GPU. Since our parallel WaveGAN can generate speech in parallel, it can achieve an inference speed 10,000 times faster than the autoregressive WaveNet. Next is the evaluation result of training time. Like we did with the inference speed, we used V100 GPU to train each model. The non-autoregressive Clarinet had to train teacher and student models in sequence, requiring about 13 days, which was the longest among the comparison. The autoregressive WaveNet took about 7 days, and our parallel WaveGAN took about 3 days, which was the shortest. Compared to the conventional non-autoregressive model, the parallel WaveGAN was able to speed up the training time by about 4 times. This is because parallel WaveGAN doesn't require two-step training of teacher and student, and the multi-resolution STFT loss is effective in helping the training of time frequency characteristics of the speech. Next, we evaluated the whole TTS framework. Here are the results of the subjective evaluation of TTS. I will play the speech samples in the order of natural speech, WaveNet, Clarinet, and parallel WaveGAN. It may be difficult to tell through the speaker, but the result showed that parallel WaveGAN can achieve performance equal to or better than the existing method, although lower than natural speech. The evaluation of WaveNet was low compared to others. One of the reasons for this was that noise was added to the high frequency band. It is known that this can be improved by using a single processing method called noise shaping, but in this comparison, such a method was not used. So please bear that in mind as you look at these results. Next, I would like to play a new speech sample prepared for this presentation. This is the result of an experiment conducted using another speech database after the publication of the research paper. Please listen to the sample. How was that? With parallel WaveGAN, you can generate such high-quality speech at high speed. Before I conclude, I would like to touch on some related methods. We announced parallel WaveGAN in October 2019. Interestingly, at the same time, another research group proposed a speech generation method called MelGAN. Although different from our approach, both are studies that apply GAN to speech generation. Related to MelGAN, there is a method that applies multi-band signal processing called multi-band MelGAN. There is WaveGAN, which has a hierarchical structure for generator and discriminator. Hi-Fi GAN, which is a time-frequency multi-resolution discriminator. Related to parallel WaveGAN, there is quasi-periodic parallel WaveGAN, which dynamically changes the model structure depending on pitch. Fast Speech 2, which has scaled to end-to-end text-to-wave, and Hi-Fi Singer applied to singing speech synthesis. Personally, I believe that the application of GAN to speech has just started and that it will grow going forward. Now, the conclusion. In this presentation, I talked about parallel WaveGAN that we have developed. Parallel WaveGAN is a method that can achieve the same or higher quality than existing methods, generate speech quickly, and require short training time. There are such benefits. We hope that this presentation has made you interested in the research of speech synthesis at LINE. If you have any questions, please feel free to ask. This is the end of my presentation. This is the list of references. Thank you very much.